Welcome back to week 6. This week we'll be covering chapter 29 on light waves. Well, we've made it to week 6 of Physics 103. You were more than halfway done with the course now, so congrats on that, making it through this far. Keep up all the good work. This week for the lecture, we'll be covering chapter 29. Your chapter 29 reading this week will cover pages 545 to 556, so we'll be skipping the last couple pages of this chapter. And then for your week 6 lab, you're going to be doing a lab report on the reflection lab from week 5. So if you click on the week 6 lab assignment link, it will give you directions on exactly what to put into your lab report, and you'll need that data from your week 5 lab. You'll also have, like most weeks, your week 6 homework and your week 6 discussion. So this week we'll be covering Huhne's principle, and it's pronounced kind of funny, not really how it looks, but also diffraction, superposition and interference, polarization, and holography. So first off, for Huhne's principle, this principle states that waves, basically, let's say you throw a rock in a quiet pool, you're going to start seeing waves appear, one wave after another. And what Huhne proposed was that the wave fronts of light spreading out from a point source can be regarded as overlapping crests of tiny secondary waves. And each wave has a new, tinier wave front. So what that means is that, let's say you have a wave, and this could be sound or light, and you drop, let's say that it's you're dropping water into a pond. Now that water, you're going to have the crests and troughs. And so let's look at these lines here. And the crests, or that peak where you see like that high point on the ripple, that crest is going to move from here, and it's going to slowly move forwards and out and out and out. And essentially what Huhne's principle is that if you reach a certain, like a wall, and there was an opening in that wall, that when that wave front hits that point, that wave front will go out in all directions. So let's say that your rock hit a wall. Well, that wave is not going to just continue straight out. It's actually going to make tiny little wave fronts that go out in a circular pattern in all directions. Now, this is the reason that sound, for the same reason that if you were to talk in a room and let's say that you were talking and your sound waves start moving through the room, and you have a wall in your house with a door through it, someone could be standing over here on the other side of the door. And the reason that sound travels to them is because of this Huhne's principle, that the sound waves disperse out in all directions. So each wave front that you have is going to cause secondary wavelets that spread out again in all directions with a speed equal to the speed of the original source of those waves. So if this is your wave front here, either your sound or your ripple in the water, then at each point on that wave front, it's going to create a new wave front that goes out from every single point along here in a circular pattern, causing that, essentially like dropping a stone in the water, causing that circular ripple that moves out and out and out. So if you were to create equally distanced waves in the water by taking a board here and dipping it at even timing up and down, up and down, up and down, creating one wave after another, one wave front hitting this line here, in this opening, remember that every single wave front is creating circular wave fronts around it. So you're getting these circular patterns all around these wave fronts. So if you have a wider opening and every single one of those wave fronts is creating a circle around it, you get this pattern here that's not really perfectly circular, but it's the pattern from all those various wave fronts creating new wave fronts. As you narrow that opening and you get down to this, you see a much tighter circular pattern because the number of points along that wavefront that are dispersing out is fewer. And so you have a fewer number of circles going out, and it ends up looking like a much cleaner circular pattern coming out of that opening. Okay, so next we're going to move on to diffraction. And we've talked about that waves can bend through reflection and refraction. So reflection would be bouncing back off of a surface at the same angle it went in. Refraction would be the bending of a wave when it goes from one medium to another, like from air to water. And diffraction is a property of all kinds of waves, so whether you're looking at sound or light, and it's seen around the edges of many different shadows. So as we've just seen with the Huggins principle, waves diffract after passing through a narrow opening. And so as you saw in that picture, the narrower this opening becomes, the greater the bending of the waves. The amount of diffraction or bending depends on the wavelength of the wave compared to the size of the obstruction that essentially is casting a shadow. So if you have a large obstruction, the wave as it hits that obstruction is going to have a pretty good amount of bending around that obstruction. If you were to have a little bit smaller obstruction in the same size wavelength, you're going to see a little bit less bending as the wave moves around that point. If you were to really tighten up and shorten that wavelength here, you don't have as much bending. Essentially, the waves are happening much quicker. It's much faster that you get from one crest to the next crest to the next crest. And so there's not as much time for the wave to bend around that object. And so the longer the wavelength is, the more bending you'll have. And also the larger the obstruction is that the wave hits, the more bending that you'll have. So light will cast a sharp shadow with some fuzziness at its edges when the opening is large compared to the wavelength of the light. And again, for the same reasons that we just discussed on the last slide. When the opening is very narrow, diffraction is more apparent and the shadow is fuzzier. We've talked a little bit in the past chapters on what happens when two waves meet up with each other. And when two waves interact, let's say you have this wave here and this wave here, both moving at the same direction at the same time and having their crests at the same point, then we call this reinforcement, and that's where you add the two crests together to get the total amplitude of the wave. Now, whenever waves meet up and interact, this is called superposition, and they call these interacting waves, when waves interact with each other, they also call that interference. And so superposition or interference can take two forms. It can take, or three actually. You can have where the waves reinforce each other and the amplitudes get bigger. You can have where the waves are going in opposite direction, or same direction, but having a crest at the same time that the other wave is having a trough. That will cancel out the waves. Or you could have different size waves and you're going to get partial cancellation. So you can see the interference of the waves pretty clearly if you were to make two ripples in a pond. So if you were to have two vibrating sources here and here, instead of just having a circular pattern all around from one ripple, you can see how these two ripples interact with each other. So you can see where those waves meet up here. You're getting that interference pattern right here. So let's say that we're looking at light moving. So the wavefront's moving this way and it hits the openings, and we know that it's going to bend equally or diffract around those openings. And what happens is you can see all those different, the bendings from this opening are going to overlap with the bendings from this opening. So eventually as these bending waves get bigger, they overlap with each other. And what ends up happening is we have points in that where those waves overlap, whereas you can see the waves sort of moving closer, and this would be looking at this wave here, like coming towards one of these waves from this opening, coming from this wave from the other opening. And as the waves from the two openings overlap with each other, you're going to get a bright area. And as the waves from if the two waves, if their crests meet together, essentially you'll get a bright area. If you have a crest and a trough occurring at the same point, you're going to see a dark area. So essentially as these waves overlap, if you were to look at that, the light coming out of that, you would actually see light and then dark and then light and then dark. So you would see something that looks like this when you have waves, light going through essentially a slit. And so you can see these dark spots and the light spots. And this would be the interference pattern that you're seeing from light going through openings and bending around those openings. So constructive interference, as we just mentioned, produces a bright region where the waves reinforce each other. So the waves are arriving in phase, or you're having two crests occurring at the same point and the troughs occurring at the same point. And then destructive interference produces a dark region where the waves cancel each other. So the waves are essentially halfway out of phase, and you have a crest occurring where a trough occurs on the other wave. Okay, so let's go ahead and do a review question. The phenomenon of interference occurs for sound waves, light waves, both A and B, or neither A and B. And as we've talked about, interference can occur with sound waves and light waves. So interference is a property that characterizes all waves. So another example of interference that you've probably seen is when you have a soap bubble in the air, the pretty colors that are on the bubble, and you get the same same array of colors if you were to, let's say, have a thin layer of gasoline on top of water. You've probably seen the colors coming off of that, and this is caused by interference. And what happens is, if let's say that this is your bubble here is going to have a thin layer of soap and then a thin layer of water, and then air on the outside. And so essentially you have air and then soap here. It would be the same thing with gas, and then water. And as the waves of white light come in to those layers, they bounce off at different points. So they're going to bounce off the water at one point, the gasoline or the soap at another point. And so when that white light hits it, the film thickness at one place might cause, as those waves bounce back, destructive interference of red light. And if you were to subtract the red light out of that white light, you would see the complementary color of red or cyan. So you'd see that pretty kind of cyan color here. At another place where the film is thinner, then you might have, let's say, you might have the cyan getting canceled out, and you'll see it's complementary of red. And the same thing would happen with gasoline on a wet street or gasoline on water. So that destructive interference will cause certain colors to get canceled out of the white. And so that's why you see the different colors on either that soap bubble or the gasoline when you have that thin film on top of some water. Let's go ahead and do a few review questions. If the thin film of gasoline was a bit thinner, the wavelength to be canceled would be shorter than that of blue, longer than that of blue, white, or none of the above. And the answer is shorter than that of blue. So if as your film gets thinner, then the wavelengths, then shorter and shorter wavelengths will be the wavelengths that are canceled out. And on the opposite, if your film were to get thicker, then longer wavelengths would be canceled out, or the colors that are on the spectrum of having a longer wavelength. If violet light were canceled by the double reflection of sunlight from gasoline on a wet surface, the resulting color would likely be red, orange, green, or violet. And the answer is orange, because orange is the complementary color of violet. If you see the color blue reflected in the interference from gasoline on water, and you lower your head so a greater angle from the normal results, you'll likely see a color having a wavelength shorter than blue, longer than blue, with a white appearance, or none of the above. The answer is you'll see something with a wavelength shorter than that of blue. So the path through the gasoline would be longer, and a longer wavelength would be canceled. The result of a long wave being canceled is a shorter wave. So you're going to see you're going to see a color that has a wavelength shorter than that of blue. So just like the ripple coming from a pond, regular light that's not what we call polarized is going to go out in all directions from a point. So just like the ripple in the pond goes out, light will move out from a central point where the light's emitted. It will move out in all directions. So for example, like an incandescent light, fluorescent lamp, candle flame. So if we were to take non-polarized light like this flashlight bulb or even sunlight, and you were to pass it through, the light, as we said, is going out in all directions. So it's going out horizontally and it's going out vertically. And if you were to pass it through a polarizer, sort of a filter that has lines going up and down like this, vertical lines, then your wave, the waves going from side to side are actually going to get canceled out through that filter, and only the waves going up and down will make it through the filter. So they're showing you sort of like a rope going through. The rope, the movement of that rope, if you put it through a fence and tried to jiggle it up and down, the rope going up and down could make it through. If you took a rope from side to side and tried to put it through this filter here, it wouldn't go through. So you're canceling out that side to side movement when your filter is vertical like this. If you were to take another polarized film and try to pass the same up and down wavelength through a film with the slits going horizontally, it would actually cancel out your wavelength altogether. So now if this was light, and you were to pass it through the first filter, you'd have 50% of your light being canceled out. If you were to have two polarized films, one going this direction and one going this direction, then you would actually see no light going through at the end.
It turns out that when light reflects from surfaces at a grazing angle, the polarized component is preferred. You know, if you're like driving and you have a road surface and the light is coming down hitting, it turns out the light that will make up the glare is polarized in the same plane as the surface. Do you ever take these scaly rocks and go out in a pond and you get flat rocks and you want to scale them across the surface? If you take the rock and you throw it kind of flat, sort of like this, okay? Boom, it'll boom, bounce off, yeah? How about you throw it like this? Kind of go down, yeah? Light does the same thing. Light that's coming down like this, bounce, huh? Light that's coming like this gets absorbed. So that's why you get the glasses. What kind of Polaroid glasses would you wear to cut out glare from horizontal surfaces? Let me show you 3 pair. Which would you use, gang? These are these for driving. You got a truck driver and you're going to drive along the road. Which pair of Polaroids? How many say they're all the same? How many say I'd wear these ones here? Squint City, honey. What's going to come through those glasses? Polaroid's light. You have to drive like this, okay? You're going to go on a cup of coffee, please, okay? Occupational, you know. Okay. No, these are what you get. See, the Polaroid glasses that you buy are usually like this, because most of the glare comes from horizontal surfaces. What if you're a painter all the time and you're painting vertical surfaces? Then you probably wear glasses like this. I don't know where you'd get them, okay? But usually the glare is horizontal, so we cut the horizontal off like that. You got like that, honey. That light come in, boom, it's okay, blocked. And now what you see is without glare. Do you know what these pair are for? 3D movies used to be popular. Used to be 3D movies where you have 2 projectors going at one time and you've got to see each scene independently. So they polarize one this way, you got glasses that way. The other projector's polarizing this way, you got glasses that way, boom. Each eye sees an independent view and 3D vision right there.
Okay, so one trick using the information that we just learned is that if you want to know if a pair of your sunglasses are polarized, then a pair of sunglasses that are polarized should have a polarizer filter, essentially, filtering out the light in one direction. So it should have, for example, polarizers going straight up and down like this, blocking out 50% of the light. So if you were to take 2 pairs of the same pair of sunglasses and hold them at 90-degree angles to each other, so to hold one lens up and then the other lens up to it at a 90-degree angle, you're essentially putting the polarized films or the polarizers on the glasses at right angles, and you should be canceling out all light coming through the sunglasses if they are in fact polarized. So if they're polarized, it will cause no light to pass through the 2 glasses, and it will look very, very dark when you look through the 2 glass lenses. If they're not polarized, you won't see much of a difference at all in the light coming through one pair of glasses compared to the other pair of glasses. Okay, that's the end of our week 6 lecture. If you have any questions as you go through your work this week, or especially starting on your first lab report, just let me know. And otherwise, I will be in touch with you again in week 7.